Augustin! Augustin!
Henri-Georges, my friend.
Who are you? What are you doing here?
Henri-Georges, if I throw an apple, it falls down. Do you realize that?
Of course I realize that.
It's crazy. Physics is still crazy.
Yes, but Augustin, that's Newton's physics. That's a long time ago. It's like in the 18th century. Nowadays we talk about quantum physics.
Yes.
With Schrödinger and Albert Einstein.
Yes.
There are plenty of things to explain, like the photoelectric effect, the duality of light, and a lot more to discover.
Wait, it seems to be very nice.
But it is.
Should we make a video to
What a
explain
great
this
idea.
to our comrades?
That's a great idea, Augustin.
Are you in?
Of course I'm in.
Let's go, let's do it. Quantum physics is one of the most complicated things to understand.
Even the most prominent scientists couldn't explain it.
But
in
this video, we will try to explain it to you.
One eternity later.
So we have noticed that if we expose a piece of metal to light, we observe electrons that are released. This would confirm the theory of the behavior of light as a wave. With the presence of ultraviolet light, all the electrons in the metal part are released. In the presence of red light, no electrons are released and the photons are absorbed. For this theory to be completely correct, the electrons would have to be able to be detached with any desired light frequency. So the question is, does light behave like a wave? Or like particles? You may have heard about the rock band Arctic Monkeys, but you didn't know they gave an answer to a question. Indeed, light can behave in two different ways, as a wave and as a particle. Crazy, isn't it? Anyway, in conclusion, the magnitude of the light frequency does not influence the kinetic energy of the electrons. This means that a photon is absorbed by an electron. Einstein discovered that light behaved as both a wave and a particle. Light exists as quanta. Thanks to this discovery, and not to the theory of relativity, he won the Nobel Prize in Physics in 1921.
If we randomly shoot marbles at a screen, a pattern will appear on the screen behind the opening. If we add a second opening, we expect a second line. Then we investigate the behavior of waves. The wave goes through the opening and creates a new wave that touches the screen. Right behind the crack, we see the greatest intensity. The line shows that intensity. But if we add the second opening, something else happens. If the top of one wave comes together with the value of the other, they cancel each other. This creates an interference pattern with many lines on the screen. Now let's go quantum. We shoot electrons one after the other so that they certainly do not collide with another electron. The electron behaves just like the marble at a crack. If we shoot at two openings, we expect two lines. What? An interference pattern. We fired electrons, but we see the behavior of waves, not particles. The electron starts as a particle, becomes a wave of potential, goes through the two slits and interferes with itself to hit the screen like a particle. Physicists decided to investigate through which opening the electron really went. They placed a camera at one of the slits, but the quantum world is even more surprising than they suspected. When they looked at the electron, it once again behaved like a particle. Two lines emerged again, and no interference pattern like with waves. The camera ensures that the electron passes through an opening, not through both. The electron behaves differently, as if it were aware of the camera. This is how the physicists discovered the remarkable quantum world. What is matter? Particles or waves? And waves of what? And what is the role of the camera? Unfortunately, we still have no answer to those questions.